Okay. In this week, we will introduce firstly the sampling theory in a simple meaning, okay? Because in the discrete time domain, we need to sample the every continuous signal in order to what? In order to analyze the R signal in the what? The computers or the microcontroller or the processors, okay? And so, firstly, suppose that we have a signal like this one, t and xt, and also we can draw to any arbitrary signal, okay? And then in order to sample this signal, we need to take a sample at each time, okay? Just like this one. And so at each time, in a simple meaning, we draw the Pythagorean right angle in here. Because if we have this information, and then we can split the signal into the parts by using these concepts. Because just using the notion of the dynamicity, in order to get the dynamic form of these things, we need to get the first order term. For example, x dot or y dot or x dot dot. This gives or produces us to what? To dynamicity in this form. And so, in order to take any sample from the continuous signal, and then we need to give or produce at each time this kind of Pythagorean right angle. Okay? This is the basic meaning in the theory, but abstract theory. Okay? And so, this is the continuous domain. And we can split the infinite number of right angled triangle, right? And so we can take a measurement from this case. And so in the mathematical meaning, we have at each case we can take measurement from the signal based on the basic theory. Just like this one. We have the x and we have the strict parentheses in here, just like this one. Ts is the sampling period, okay? Which is dependent of the time in here and in the index of the R terms. And so xt can be summarized or discretized or sampling from the n ts at each case. And also we need to take that this n is an integer part of this study, okay? And so ts also a sampling period, right? This is a simple case in the microcontroller or in the programming techniques, and then we can take the discrete values or the sampled values from the continuous one, okay? But we have 4 definitions in this domain, in the sampling domain, to convert any signal to discrete one, which is a topic of this lesson. Firstly, we can draw the continuous signal, just like this one, x and t, and also we can draw just like this one, okay? And so x is the variable or changeable at this case, and so t is also variable in here. For example, we can take the 1 or 1.2 or 1.45, and so we don't have any fixed sampling signal in here, which is calling to the continuous one, okay? This is the definition of the continuous signal. If the x is variable or changeable in time and t is also changeable in here, and then we can say that this is continuous signal. This is the general meaning of the continuous one, okay? But this is the A case, and in the B case, we can convert this signal based on the what, the x and t in here, just like this one. What's the definition of the signal? Have you heard of it? Have you seen of this signal? In this case, we have the x is constant, right? In the definition. But t is variable, right? This is the quantized signal form. Okay? This is the definition of this one. Okay? And so if the x is constant at each time and t is also variable, for example, this is taking to what, the 0.2 second in here, but this is what, the 0.01. Okay? This is quantization of the any continuous signal. And so the ADC module, analog digital converter, can use this formation in order to quantize the R signal formation. But with what? Variable t, or the time parameter. Okay? Okay. And after that, if we take the continuous signal and convert to the quantized one, and then we can write the any other form in here, or the next form in this case, just like this one, x and t in here. And so we can generate this kind of signals in here. Okay? And so, what's the meaning of this signal? Or what's the name of this signal? No, this is not discrete signal. Because if we have the quantized signal in here, just like this one, this x is constant in here. Okay? But t is variable right now. But we take one sample from this whole time coming from the what? The t, right? And so this is called the sampled signal. This is the definition of the sampling. We don't have the many points for a given time period right now. We have one value, okay? And so, after all this case, we have the t and x value in here, and also we have this kind of periods, just like this one, okay? And so, if we have the any signal formation in here, just like this one, t is constant, x is constant coming from this signal, and so this is digital one. Okay? You get the point of the definition of this signal: continuous, quantized, sampled, and the digital one. Any question about that? Ayça, you understand everything what I'm saying in here? Oh. Any question? Hakan? In the D, yes. Because if we have the one sampled value in here, for example 0.2, 0.1, 0.2, 0.1, 0.05 or 0.2, okay, in this sample. But in the digital one, we need to give or generate the fixed period time. For example, 0.2, 0.2, 0.2, 0.2, 0.2. These are the process to converting the signal to the what? To the digital one, okay? It's the basic difference which is given in here, okay? You can use the sampled signal, but in the sample signal, we don't have the what? The time period or the fixed time period, which is the utmost important for the what, for the controlling technique or the signal processing in the microcontroller or the computer structure. This is so important. Okay? And so, any question, Ayça? No? Okay. So, this is the basic definition of this term. But in theory, we take this measurement with a special operator. Because if we have the math and its rule derived from the what, the Pythagorean theorem or the any other mathematical rule, and then we need to formalize everything based on the mathematical rules, right? And so, in the basic meaning, what is sampling? The sampling is converting continuous signal to digital one. Okay? And so, if you have the shape of the A, B, C, D procedure, contains the whole the what or creates the what, the sampling procedure. Okay? But in the microcontroller or the computer structure, we automatically do that because the ADC converter can automatically update the R signal with the what, the quantization, sampled, and the digital one. Okay? Has a cyclic period to contain or to get the what, the continuous signal from the real life. Okay? So, ideally, we have sample from the what, the impulses. What is impulse? Have you heard of it? What's the meaning of the impulse? Yes, peak, but why? It has a peak. Why do we need to use that? The impulse is the most important signal in the signal processing. No. No. Any thoughts? Okay, and so this is special signal. The impulse in continuous time creates the what? The infinite value at the zero. But with one important parameter or the condition that's satisfying with what, the minus infinity to infinity values in here. And so if we have any impulse signal in here, which is equal to the what, the 1. Do you remember that, Ayça? Ayça, stop. You don't remember anything about signal processing. So how can I taught these things? Say something. Okay. And so, this is what? This is area for. Right? This is the unit area. And so, we can use the impulse signal in order to what? In order to obtain the specific time value from the X signal. Because it creates the what? The spike. Goes through the infinity. But with one condition, which is the integral of this term must be equal to the 1 or the unity value. Okay? Just remember these things because it's important to create the linear time invariant system or the any system dynamic equation, which I will prove in this lesson. Okay? So, this function returning always present value for a given signal due to what? The energy constant in integral domain, because it's a unity signal, and so it does not change anything applied on this signal form. Okay, just remember that. And so we can write this x sampled or the digital signal based on the what? The xt times ts t. Okay, and so if we have this kind of function, and then we can sample, or we can take the digital value of the what? The continuous one. Okay, but in real life we need to utilize the what? Some specific environments or the devices to build this nomination, which is given in the theory, right? And so in real life, the ADC module just use this function, apply it on the signal. Okay, ADC just only using the what? These terms. And so if this is the case, and then we can take the what? This continuous signal in here, just like this one, and so at each time we have the spikes in here with these values, right? The TS, 2TS and 3TS. Okay, but on the other hand we have the what? Impulse signal, just like this one. Okay, but this is the representation of the what? Discrete impulse response, right? This is equal to what? The 1 if n is equal to the 0 and 0 otherwise. Okay, and so we can build this algorithm in the what? In the microcontroller structure, or the in C or C++ programming language. And so this is the direct utilization of the what? This area form can be converted into the what? Into the one line or one spike with the values of the what? The 1. Okay, this is identical in this case. Okay, and so if we take the any signal, just see that this x is existed in the environment, but if we apply this impulse response or impulse signal to this one, and so we can take the feature of these terms. See? So how can we create the continuous one of this object? X star impulse can be written just like this one. Do you remember that? This formula? Convolution, right? This convolution. And so plus, and so x tau value and t minus tau times d tau, right? And so if we have the any signal, and then we can use this impulse or continuous impulse signal to what? To get the nature or the feature or the roots of this signal coming from this integral form. Okay, this is known as the what? The convolution. Okay, if the sampling period in the discrete time, we should use the what? The quantization or the sampled or the digital signal at each phase. But in the continuous one, we can sense the world or the signal by using the what? Using the continuous signal. In the first place, we use the what? Discrete one, discrete function. But in this case, we can also build the what? The R output by using two continuous functions. İşcan, you must work hard. Okay? And so this is so important because we have talked about the root or imaginary or the Fourier transform or the everything about the what? About creating the time. But we do not know right now to what? How to obtain the information coming from these forms or the time dependent form or the time period. And so in order to do that, we need to use the convolution, and I will prove that in here. In the section 2, we mainly focus on what? Convolution, or its integral form. Okay, section 2, convolution. Okay, and so the convolution is defined with the what? It's a simple mathematical operation. Expressing relationship between the what? Two continuous signals. To produce an integral. Why integral? Just guess it. Why we need to use the integral form? Yes. And so if we change the dimension, and then we can have the what? Different property, right? Right? Just remember the energy form of this term. So we can transfer the kinetic energy to the potential one. Why? Why we can change the kinetic energy or convert the kinetic energy to the potential one? Because it's energy, right? And so we can easily transfer the energy to the another form. But energy has a beautiful property. Energy is always defined with the what? With the area form, right? Because the Pythagorean theorem proves that we can relate to what? The one distinct feature with the another one. And so this is also produced what? Integral. Why is integral? This is so simple answer, because X is a different property, impulse is a different signal, and so if we have these two signals, and then we can relate these two signals by using the integration form or the integral form. Okay, we can consider that the X is an energy and the impulse is an energy, and so we can produce another form of these terms based on the integral one. Okay, and so if we have the derivative or the time dependent system or the integral system, and then we can create the sum outputs to represent these formations in here, just like this one. Okay, any question? Ayça? No? Okay, so we should write the theorem for 1. The convolution of two signals x, t, h, t is derived by yt is equal to xt and ht star operator in the form of yt is the output signal and x tau times ht minus tau d tau. Okay, and so this is called the system impulse function. Okay, and where xt is the input signal, ht minus tau is the impulse signal, okay, and yt is the output. This is the theorem for the what? For the convolution operation, okay. So this is the basic meaning in here, but we just see that if we have this formation, we can relate or we can change the function x and tau, or x change with what? The h. We have the duality in here, just like this one, okay. We have the potential energy and the kinetic energy. We can convert the kinetic energy to the potential one, or we can convert the potential energy to the kinetic one, right? This gives us a duality, potential to kinetic, kinetic to potential, and so this convolution also provides this formation, okay.
What tau refers to? Tau, what refers to?
What?
Tau here. Yeah, time is time, but tau here. What is tau?
Tau.
Yes.
I will see that. I will show this implementation of these terms. If we have the any signal, and so we have also a template, okay. This template, just like this one, it's a bottle, okay. This is a template. This is an impulse response. Just give me. In the template, we have this function, which is calling the x, and so this is the what? Impulse response, okay. And so at each time, tau increase, and so we yield what? The 0, 0, 0, 0, and after that, this template is compared with this another signal, just like this one, okay. And so if this is the shape is similar with the other one, and then we can say that we have 0, 0, 0, 0 and 0 0.2, 0 0.4, 0 0.5, 0 0.6, blah blah 1, 0 0.9, 0 0.6, blah blah blah, okay. And this is the convolution. And actually in the real meaning, the convolution is the similarity rate of two objects, okay, two objects, but one of them is considered as a template, the another one is an input. In the same way, we get the same results from these nominations, okay.
The real value of tau is just 1 point.
No, because if we have this template function, at each time we compare with the 1 values, okay, but the t is, for example, at the t equal 1, we can compare this signal. After that, we can assign the t to 2, and then we can generate another response. And after that, if we add the whole this response, t equal 1, 2, 3, 4, 5, 6, and blah blah blah, and then we get the what? Total signal, okay. So, but in the real life, this is the similarity function. We can compare the any signal based on this one. For example, what's your name? Baran. I see Baran. Baran is human, okay? And so I learn the Baran in my mind, okay? This is an impulse for the human. And I see the what? What's your name? Hassan. Hassan. And so if I have the definition of the Baran in my mind, which is an impulse signal, and then I compare the whole results with the what? With the Hassan. And so Hassan is also human. And so I convolve at each time by using my eyes to what? To define your pattern. Okay? It's a time-dependent pattern. But I could say that this is also human. But if I see the Ayça, and so Ayça is similar with the Baran at the rate of what? The 0.6. Ayça is also human, but Ayça has different property in here. And so I need to what? I need to build another function for the Ayça. It's a woman, right? Ayça? Do you understand what I'm saying, right? Okay. Thank you. So, do you understand these concepts? The convolution operation. In the signal formation, we can formulate these terms in the mathematical formation, just like this one. This is a huge simple idea, but we can generate the what? Everything using these concepts. Okay?
Yani hocam yanlış anlamadıysam şöyle bir şey. Benim Baran olduğumu biliyorsunuz ve
Yes.
benim İhsan olduğumu da biliyorsunuz.
Yes.
Hasan'ın Hasan olduğunu bilmiyorsunuz ama Hasan'a baktığınızda bir İhsan'a benzediğini biliyorsunuz.
Yes.
Ve bu yüzden kafanızda Hasan'ın İhsan olduğu canlanıyor.
Yes, I have an impulse signal.
Baran olmadığını bilmenize rağmen İhsan.
Yes, because if this is the case, I have the similarity rate with the 1 in the integral form, right? Hakan? Is everything okay for you?
Şimdi Hasan'la Baran örneğini verdiniz mi?
Yes,
Aynı şey sinyaller için de mi geçerli?
definitely. Otherwise, we cannot write this theorem because we all examine the universe, finding the similar pattern, and then I can formulate all the things in the math. And so this seems too complex, but it's not. Okay? It's not. It's also simple.
Yani buna indirgersek benim kinetik enerji olduğunu biliyorsunuz. Hasan'ın da bir enerji olduğu belli ama ne enerjisi olduğu belli değil.
Yes.
Onu bulmaya çalışıyoruz.
In one domain of signal, and so I have the one pattern for the human, but also you have noise or the hands. Okay, I have also this distinct impulse signal for what classified as a human or the hand or the glass, right? So, but in the maths, we just only use to some simple functions. For example, in the example form, how can we do that? They consider two functions. Xt is equal to the exponential t times ut, and ht is equal to ut. Okay, and where ut is equal to 1, t is greater than 0, and 0, t smaller than 0. Okay, and so our question is that find the what? The convolution of these two signals. Okay, and so solution is simple. We just use the what? The convolution integral. Is yt is equal to the what? Minus infinity to infinity, and e minus tau, right? This is the xt signal, and u tau, right? And times u t tau times d tau, right? And so if we have this nomination or this signal, and then we can say that this is true for the t is equal to what? 0. Otherwise, we generate the results of the what? 0. And so this is simplified in this form, 0 to up to now, Hüsamettin, t, right? If we take this integral up to t, and then we can generate the r form, right? No, because if we have the t value in here, we functionalize this signal up to t. Okay, you will see right now. Okay, and so this is e over minus tau d tau, right? And so if we take this integral in here, just like this one, yt is equal to the minus exponential tau with the what? T and 0 value, and so this yields the what? The exponential t minus e0, which is equal to what? The 1 minus e t, right?
Mu of t minus tau. What is it?
Huh?
This
This is also 1 in here, because if we take the what? The 0 value in here, and so this automatically produces the what? The 1. because the R function is 1.
We take tau as 0.
Uh-huh.
So t can be
This t minus tau is always going to what? 1 in here, because we create a bounded integral in here. Because the ut, if the t is smaller than 0, and then the ut is always 1. Okay? Yes, this is simple. And so, this is our solution for the what t is greater than 0 value. Okay? This is how we can convolve this two signal based on this information. And so this integral form always produce us to what? To this function. Right? Okay. Answer. But this is the continuous one. We have another theorem in here. Theorem 4.2. Okay? And so the discrete convolution of two signal x n h n is the index is derived by with the what y n is equal to x n h n, right? And so in the form of to what y n x n star h n is equal to what? The summation formulation minus infinity to infinity value x n times h n minus key, right? This is also what? Impulse signal. In discrete domain, we have one line form, okay? And so we can write easily this sequence to what? To define the discrete time convolution, okay? And so in the example form, just assume that xn is equal to the what? The 1, 2, 3 in here, and hn is also considered as the what? The 1, 1, 1. It's the unit signal, right? It's always the 1. And so our formulation is that for the solution yn is equal to the what? Summation k minus infinity to infinity value xk times h n minus k, right? And so we can bound this signal based on the what? K must be equal to what? 0 and otherwise 2, right? We have the 3 signal in here, right? 0 to 2, okay? Okay. So n is 1, 0, 1, 2 in here. And so we don't need to use the what at every point up to infinity values, because we have only present values for the what? The 0, 1, 2, right? Okay? Okay. Huh? No, this is a unit step response, okay? And so before the what? The t is smaller than 0, or the sequence is smaller than 0, and then this yields to 0, okay? That's why we just use this formation h minus nk. And so for n0 we have y0, which is equal to the what? The 1 times 1 in here. And so the other terms is the what? Is 0, because the k is greating what? The for the n is 0, and then 0 h0 gives us 1, but the otherwise minus 1 and minus 2, and the other term is the what? Equals to 0, okay? But in the for n equal 1 we have the y1 1.1 and plus 2.1, this equal 3, but the two term is not equal to this one because this has the negative index in here. Because the n is 1, if the k is 2, and then this yields us to what? -1, which is 0. Okay? But in the what? For 2 and y2 is equal to 1.1, 2.1, and 3.1, right? And so this is equal to what? 6. And so y 0, 1, 2 value is equal to the what? 1, 3, 6. Okay? This is the basic formulation for the what? For collecting the whole the terms in the discrete convolution. Okay?
Zaten her zaman hiç sıfır alıyoruz.
Aha.
Her zaman hiç sıfır alıyoruz ya.
Aha.
Neden 3 tane kullandık sadece
Because this is an arbitrary, it's a random example, but in every case, that not might be the condition of these terms. Okay? This is the basic idea for the what? For calculating the discrete convolution. Okay? And so we need to take a break, and after that we will start at 2 p.m. Okay?